And that's kind of the problem with TCP.
What about hackers? Because is that connection ID not exposed?
And that's the question, right?
This is going to make a lot more sense. Hey everyone, it's David Bombal, back with a very special guest. Robin, welcome.
Hello, David.
It's wonderful to have you because I believe things have changed recently on the internet, which affects all of us, right?
Exactly. The introduction of HTTP3 will have massive repercussions in the coming years. So important to get to know right now.
I saw you tweet about this, and that's how we set this call up. So tell us kind of like what's happened briefly and why do we care?
Interestingly, it's already been affecting you for quite some time. HTTP3 has been in the works since 2012, started at Google, who deployed it widely for Google Search and YouTube. And then they transferred it to what is called the IETF, the Internet Engineering Task Force, the organization that actually standardizes protocols. So a lot of people from like Mozilla, Microsoft, Facebook, several bigger companies came to join in to specify what this new HTTP3 and actually the underlying transport protocol called QUIC that we're going to talk about should be. And the idea is that these are like next generation protocols that are very evolvable towards the future. And they've actually been deployed at wide scale since 2018 already. And a lot of browsers already have support, and about 1/4, so 25% of current internet traffic, at least for the bigger companies, is already HTTP3 and QUIC. So if you're watching this on YouTube, big chance you're already using HTTP3 right now.
Are you helping write the standards, or what's your sort of involvement? I know I've seen you say you've been doing this for quite a few years.
So I started as a PhD researcher on HTTP2, looking at its performance, and then just as I was doing that, HTTP3 was starting up at the IETF, and so I was able to kind of organically roll into that, and I was able to actually contribute quite a bit to this effort. I mainly made a lot of debugging and analysis tools. Yeah. Think about Wireshark, but then very specific for QUIC and H3. And if you scroll down to the HTTP3 RFC, all the way at the bottom, there's a long list of like people involved, and quite proud that my name is on there. On there as well. So I wouldn't say I had the biggest impact there, but I've definitely been involved for like, I think over 5 years now.
Let's start with the RFC thing. What's the RFC for HTTP3? But it's like, there's quite a few of them, isn't there?
This is where it gets somewhat complicated. HTTP3 itself is one RFC. It's 9,114. But it's actually comprised of several other RFCs you also need to make the total package work. The two main ones you need are also called QPAC, which is header compression. And then there's also a new extensible priorities RFC that kind of works for both HTTP2 and HTTP3. And so you need that to get like optimal performance. And the reason why HTTP3, its standardization was delayed somewhat, because for example, QUIC, the underlying protocol, has been standardized for a few months already. This was delayed because they have also done like a major reworking of HTTP1, HTTP2, and then they've kind of split out like common concepts in two new documents called HTTP Semantics and then also caching, separate document. Those were previously coupled very tightly with HTTP1. And so now they decided to like clean ship, clean house, do everything correct in their separate documents. They call it a cluster, a big cluster of different HTTP related RFCs. And that came out like exactly 3 weeks ago now.
Wow.
It was finally standardized, yeah.
Like you've mentioned QUIC and HTTP3. Is it the same thing? Is it different? And how does it change things? So I just want to give you the floor. And if you can like kind of explain the rationale to getting here. And like, I see you got UDP there. Why is there UDP? Why are we not using TCP? So a bunch of random questions, but like, what is QUIC? What is HTTP3? Why do we care? Why are we using UDP, etc.?
Lots to unpack. Let's start at the beginning. What is HTTP3? And why do we need it especially? That's a question I get a lot because HTTP2 has only been from 2015. That's not too long ago, right? And as you can see in this slide, I like this slide because it really shows that HTTP2 and HTTP3 are really quite similar. They do very similar things. There was a much bigger difference between HTTP1 and HTTP2, but 2 and 3 are much more similar. So why in hell do we need HTTP3? It's really not HTTP3 we wanted QUIC. And what is QUIC is actually more intended to be like a replacement for TCP. So TCP, your bread and butter protocol that most things on the internet use, that is something we have wanted to upgrade or replace for a long time, and that is now finally here with QUIC. And originally the idea was that we would just run HTTP2 on top of QUIC. that was just going to be like a swap out replacement, as is intended by this whole layered protocol model. In practice, that turned out to be way too difficult. And so we kind of made a new version called HTTP3. It has exactly the same features as HTTP2, I should say, but implements them in a very different way. So the practical details are different. The high-level features are almost exactly the same.
So why do we have QUIC?
So QUIC, and this is an interesting one, TCP has been around since, like, say, the 80s, right? And it served us very, very well. But there are some downsides that we want to mitigate. And a good example of that is connection setup time. So as you probably know, TCP starts with a three-way handshake, the SYN-SYN-ACK handshake, and that takes a full round trip on the network. And especially if your client and server are far from each other, that round trip can take about, like, say, even 200 to 300 milliseconds. And it's not just that. After that, you get also the TLS handshake, which in older versions of TLS took 2 round trips. Luckily, with the newer TLS 1.3, we got that down to just 1, but it's still 1 additional round trip. And it's only after that that you can actually start doing HTTP level requests, like send your first request and get response back. So in these situations, even with TLS 1.3, you're waiting for 3 round trips, sometimes over half a second before you get useful data back. And that is somewhat logical. If we go back historically, we of course wanted to run HTTP1, for example, with and without TLS on TCP. Right, you had HTTP plain text and then HTTPS, and you could just swap out TLS or just leave it out. So that was logical, and that's what led to this setup. Everything is nicely and cleanly separated. The protocols don't need to know about each other to function. But it's inefficient, because what you really want is kind of like the third column here, where you would actually want to combine the TCP and the TLS handshake in a single round trip. And what you actually want is the fourth column. Why can't we just do everything at once? Single round trip, everything is as fast as it can be. There is no technical reason why we can't do that, because QUIC does exactly this. So what they tried to do was integrate this into TCP. TCP originally can't do this, but they were like, okay, let's just make a new TCP extension, which is called TCP Fast Open. And TCP Fast Open says, okay, normally in the SYN-SYN-ACK, you cannot send data. The SYN and SYN-ACK packets cannot contain data. They're only the TCP headers. New extension Fast Open allows you to carry data, and so you can put in there the TLS data, and even if you want HTTP data as well. Fine, everything happy, everything is more efficient now. That's not really what happened, because what happens on the internet is it's not just your client and server. In between are a lot of what they call middle boxes, other appliances that also speak TCP. One of the best examples of this is a firewall. And a firewall is going to look at the TCP level data and try to figure out, is this a legit connection or is there a hacker trying to do something that's not correct? If you have a firewall that was implemented before TCP Fast Open was thought of, that firewall is going to see, okay, TCP should not have data in their SYN packets. Suddenly, I see connections with data in the SYN packets. That's not okay. That's probably a hacker trying to do some nasty stuff. I'm just going to drop these weird SYN packets. And so, when they try to deploy TCP Fast Open, which has been around for almost a decade, I think since 2012, this was standardized, a lot of connections simply fail. They simply get dropped at these middle boxes. And so it has taken almost a decade for this kind of optimization to be introduced into TCP proper. So it kind of works now. It still doesn't work well enough for big browsers to enable it, but it sort of works on most networks by now. And so the idea for QUIC is then, if we want the next big feature, we don't want to wait a decade. We want to be able to deploy this within months of us needing it. And so we want to do something new. And so this is basically the big thing that QUIC changes as opposed to TCP. What QUIC is going to do is going to deeply integrate with TLS. TLS is no longer an optional protocol. It's no longer layered on top of QUIC. It is deeply integrated inside of the protocol.
HTTP 3 is always encrypted, is that right? Unlike
yes,
HTTP 2, yeah?
Absolutely.
Okay.
Now, HTTP 2 conceptually could be done plain text, but no browser ever implemented that. So in practice, HTTP 2 was also always encrypted, at least for the browsers. But so HTTP 3, yes, there is currently no way to do this unencrypted. And this is not really to provide better encryption of your user data, because that is already fully secure with HTTP 2 as well, right? All your passwords, all your emails are perfectly safe. What QUIC is going to do is it's also going to encrypt the transport level headers. In TCP, you have things like packet numbers or sequence numbers, acknowledgement numbers, flow control windows, that kind of stuff. All the things that are in a TCP header, those are plain text visible on the wire. With QUIC, that is no longer the case. As you can see here, we encrypt much, much more of the transport level stuff, including things like packet numbers that were usually visible. The reason for that is, again, the hope that if the middle boxes cannot read this data, because encrypted data looks like random data to outside observers, if they can't read it, they can't interpret it, and so they can't break if we ever change QUIC to have like a new field in there or a different extension that we want to add. The firewalls can't read it, so they hopefully won't drop it if it's something they don't expect.
Is that the same reason why you use UDP rather than just having QUIC directly on IP? Is that kind of the logic because of these middle boxes?
Yeah. And that's exactly the same reason. That's always a question people, a misinterpretation I've seen. They say like, okay, they use UDP because it is faster.
Yeah.
And that is completely not true. Because QUIC basically re-implements everything we have from TCP, everything that makes TCP conceptually slower than UDP. It re-implements it. We have congestion control, we have connection setup, that kind of stuff. UDP is only used because middle boxes, again, don't expect anything else than TCP or UDP directly on top of IP.
So it's a myth to say that, HTTP 3 is a lot quicker than HTTP 2, or is it kind of quick but not really that quick? Is that right?
No. It is faster, but it's not because it's using UDP. It's because it's doing smarter things or doing more things. What I will show you about the connection setup in a moment, that is why HTTP 3 and QUIC are faster. It's not because of UDP. UDP is only there, again, because middle boxes expect TCP or UDP. If we try to run QUIC directly on top of IP, that's possible. There's no technical reason why that's not possible. But practically and deployment-wise, you would also, again, have to update a lot of those middle boxes along the way to suddenly expect that. And they said, let's not do that. Let's just run it on top of UDP because most appliances, if they maybe they don't allow UDP yet, but at least they speak UDP. They know what UDP is. That's indeed two things. We run on top of UDP and we are deeply encrypted, mainly to prevent middle boxes from messing with our traffic. And that allows us to be much more flexible in the future. And that's also why we can't just have a TCP 2.0, because that would take years to deploy, right? As we've seen with TCP Fast Open. And there are several other TCP extensions that we've tried over the years that also fail to quickly find sufficient deployment. One example would be TCP Multipath, for example. QUIC is much more flexible, and the TLS integration means that we can do in QUIC standard what we wanted to do with TCP all along. So if we look at the QUIC's basic handshake, that's the third column here, it is always going to combine the QUIC transport level handshake, basically the QUIC SYN-SYNAC flow, and then the TLS handshake is combined into a single round trip. So that's how QUIC is already 1 RTT faster on average than your basic TLS, your basic TCP stack, not because of UDP again, but because it combines the two. And it can then, interestingly, go even further. What we really wanted, as I said before, was something like here on the right side, right? Combine everything into a fully complete round trip. And that's now actually possible with QUIC, with a feature called 0 RTT. And the idea there is that the first connection you have to a QUIC server that you haven't seen before, that has to do the 2 handshake. But during that connection, you can actually negotiate encryption keys for the next connection after that. And so if you do a next connection to a server you've already known and you've remembered those encryption keys, then you can immediately encrypt your first HTTP request in the first round trip. And so you can combine all 3 layers, the transport layer, the security layer, and the application layer, all into a single round trip, basically, and get a lot of data in earlier. And that's, I would say, the killer feature of HTTP 3 and QUIC. There are other performance optimizations that we'll talk about later, but this is like the main one, the one that most users probably will find impact on, the most websites will find most impact from this one. One nuance I want to add is that 0 RTT is not a QUIC only feature. It's also something you can use with HTTP 2 because it's a TLS feature. So you can also do this for the TCP stack, which is great. You can also speed that up. You just won't have like the nice 1 RTT for everything. You will still need 2 RTTs because we can't combine the TCP handshake with other things because TCP Fast Open is difficult to deploy.
I've read on your blog, you said this something along these lines, that this is replacing TCP with QUIC and then you get HTTP 3 as a bonus kind of thing. Is that right?
Yep, I would say that's correct. The idea of QUIC is to replace TCP for the future, to make it more flexible in the end. HTTP 3 is not really a bonus, it was more like a necessity. Because we can't run HTTP 2 directly on top of QUIC. HTTP 2 apparently was designed with a little bit too much reliance on TCP specifics that QUIC broke, that we can talk about in a second. And so it was too difficult to just keep it. And so HTTP 3 is just something we need to be able to use QUIC practically.
To get the benefits like faster connection setup, well, I mean, it's been tried to rewrite TCP or add features to TCP, but it was taking forever to get the middle boxes to support this stuff, like the routers and the switches and the firewalls, really, I would suppose, the big one. So it made more sense to create a new protocol. So QUIC is like TCP version whatever, like a brand new protocol. You had to use UDP because otherwise the middle boxes wouldn't support it. And then to use QUIC, you had to get HTTP 3 because HTTP 2 doesn't support all the stuff of QUIC. So that's kind of like big picture. Is that correct summary?
I think it's a perfect summary, yeah.
The first big killer feature is the QUIC setup, yeah? Rather than going like three-way handshake and then like a bunch of other stuff sent between, in the best case scenario, it's like one to server from client and then back again and we're done, yeah?
Exactly, that's right. That's the first big feature. The second big feature, and maybe that'll give you some insight in why we couldn't just reuse HTTP2. You can see that here on the image, the stream multiplexing. In HTTP2, that was part of H2, and now that has actually moved into QUIC to reduce something called head-of-line blocking.
Yeah, I've seen that used a lot. Can you explain that?
This is a bit technical, so let's see if I can explain it correctly. The idea is that TCP, so the second row here, TCP, as you may know, it doesn't actually have like packet numbers. TCP has sequence numbers, and the sequence numbers mean this TCP packet carries between byte, let's say here a byte 450 and byte 749 in a specific byte stream. So basically TCP thinks it's only carrying one byte stream, in practice just one resource. One file is being downloaded over TCP. That's how it was originally designed. For websites, that's of course not the case. We don't have just one resource, we have multiple. In this case, we have two. We have a CSS file and a JavaScript file. We both want to download those over a single TCP connection. And you can't do that because TCP doesn't allow you more than one resource at a time. That was one of the big problems with HTTP1. And so what HTTP2 did was say, okay, we're just going to abstract that away, and we're going to introduce the concept of independent byte streams at the HTTP2 layer. So as you can see there on the top, what HTTP2 actually does, it injects, like, they call it frames, but it's really like a mini packet. Like a mini HTTP2 packet gets inserted there. And this says, for example, the data frame is called, it says the CSS file is a stream with ID 1. And the JavaScript file is a stream with ID 2. So those are different. 1 and 2 are different, and so we have separate resources. This means that when you get this data back, the browser can decode this. They can know, okay, the coming 450 bytes are CSS. The ones after that, the 300 bytes after that, are JavaScript. And so they need to be handled differently. And that works fine. TCP doesn't have to know anything about this, and we can still send multiple resources on one connection. The problem becomes, what happens if this middle TCP packet is dropped? There's some problem in the network, the center packet is lost, but the third packet, it does arrive. And so now, conceptually, at the HTTP2 layer, we know, and the browser knows, that the CSS stuff is actually not interrupted. CSS, we had the first 450 bytes, and in the next 550 bytes, we have that. Those are there. We can actually just process all of our CSS data. It's only the JavaScript that has been delayed, and that's the only one we should wait for the retransmission to come in. We know that at the HTTP layer, TCP does not know this. TCP thinks it's only sending one file. It only has like 1 byte range there. And so it loses a full byte range 450 to 749 there. It doesn't know any data after that might be independent from that central packet. And so what it has to do is it has to be conservative. It knows the sender packet is lost. Everything after that might depend on the sender packet. I'm going to have to be careful and just not process anything after the lost packet until the retransmission comes. You leave a little bit of performance lying on the table because the CSS could have been processed before the retransmission came. And this is what is called head-of-line blocking. So the packet lost is at the head of the line, the head of the packet line, and you have to replace it at the head of the line before everything else can proceed.
So in other words, the CSS gets delayed even though it's not necessary to delay it.
Exactly.
While we're waiting for that piece that went missing to come back. The header line, like you said, that initial packet is delaying all the others from being processed, even though they could have been processed, right?
Yeah. That's exactly the problem.
It slows things down again.
It slows things down again. Not necessarily slows it down in a huge way, but it is less efficient than it could be.
Yeah.
Right? You could squeeze more performance out of it. That's the way I like to look at it. And so basically what QUIC does is it takes this concept of these streams, so the stream IDs that we had in HTTP2, and it takes those from the HTTP layer and it brings it down into the transport layer. And so you get a comparison like this, where this stream ID stuff and tracking which bytes belong to what stream, that's no longer done at the HTTP level, this is done at the transport level. So now QUIC suddenly knows there are multiple independent streams going over the network.
Oh, I see. Yeah. You've moved it down. Yeah.
We've moved it down. QUIC no longer has sequence numbers. QUIC has actually proper packet numbers, packet 1, 2, 3, not sequence number that are sometimes difficult to follow in something like Wireshark. QUIC has nice packet numbers, very used. QUIC uses what are called stream frames, which are basically saying, okay, for this stream, we now have byte X to Y. So in this case, byte 0 to 449. That's for stream 1. The next packet carries JavaScript. That starts again. That is again byte 0 to 299 because it's specific for that JavaScript stream number 2. An important note to make that I like to make also is that QUIC doesn't need to know about JavaScript, CSS, what exactly is in these streams, of course. It's not that tightly coupled. It just needs to know these are independent things that are going over my single connection. Why? And this is where we get to the fun stuff, right? If in QUIC, here the second packet is lost, QUIC will then receive the third packet and it can see, okay, the first packet had byte 0449 for CSS, and this third packet just starts at byte 450. So there is no gap for the CSS. And so, hey, why wouldn't I be able to process the CSS? Because I have all the data, the full byte stream of CSS is intact. For JavaScript, it sees, oh, this suddenly starts at byte 300. I haven't gotten bytes 0 to 299 yet, because that's in the lost packet. So it blocks the JavaScript file, but it passes on the CSS data to, for example, the browser for processing.
In TCP, if you're the server, let's say, and I'm the client, my client would set up a connection to your server. So that would be one connection. And within that connection, I've got these little streams, which are like, I don't know what the right term is, but like stream is obviously the right name, but like many connections within that one main connection, right? But TCP is not clever enough to like handle that if one of those goes missing. In QUIC, we've still got one connection, multiple streams, but just the way that it's been implemented, QUIC doesn't slow things down when one of those streams has a problem, like many connections has a problem, correct?
Yep, exactly.
And the reason for doing this is if you connect to a modern web server, you've got a whole bunch of different files. Rather than downloading them sequentially, you want to be able to download them in parallel, hence the idea of streams. Is that right?
Yeah, you want to download them chunked, interleaved in many different ways.
Great.
To get more performance as well there. So that is one of the main ways that this works. This then leads to other QUIC benefits like smarter loss detection and usage. QUIC doesn't need to retransmit full packets. It can retransmit parts of packets if it wants to. And this is one of the key points, I think, that makes HTTP3 plus QUIC faster, is that QUIC can, for example, in HTTP3, we will have a concept of stream priority. So some files are going to be more important than others. Your JavaScript and CSS are going to be more important than the image file on the bottom of your page, at least in the beginning. So if you have a packet loss for both the JavaScript and the image file, in TCP, it wouldn't matter. It would just transmit it in the order they were originally transferred. In QUIC, you can make much smarter decisions. You can say, oh, the JavaScript file is much more important, has a higher priority. I'm going to retransmit the lost packets for the JavaScript file first so that they can be processed first, and later I will retransmit the image. I can even delay the retransmissions for the image until after the CSS is done, or until after higher images have been discovered and processed. This allows for a much tighter integration between HTTP3 logic, with us knowing some files in a web page are more important than others. And that then directly impacts, for example, retransmission logic, loss detection logic at the transport layer through this stream mechanism.
Who decides what's more important?
Yeah, so that is a wholly different topic.
Okay.
And I've got this next slide kind of tries to show you how difficult this can get. So here, each row is a different way of doing prioritization, and each color is a different resource, as you can also see in the legend at the bottom. And there are many, many different ways to do this. You can say that the JavaScript files are all more important. You can say the fonts are more important. You can say it depends where the JavaScript file is in the web page. If the JavaScript file is async or defer. Many, many different ways of doing this. And browsers now, even if you're a front-end developer, you can use features like preload resource hints, or things like priority hints, or image lazy loading attributes, if people are familiar with that, to explicitly tell the browser these resources are more or less important for my specific page. And that then influences how this prioritization is done. To answer your question, the browser has like a basic set of rules that it thinks these things are more important most of the time, and then developers can actually influence this in small ways. using using HTML and JavaScript APIs for that. And that then also influences how this is actually sent on the wire, as you can see here. But prioritization is a is a much more complex concept. I don't think we want to dig too deep into that today.
No, I mean, the fact that you said that the browser has stuff built in and the developers can kind of influence it, that's enough, I think, for us to know. It's just good to know that that's possible. Yeah.
Exactly. And so to get back to this, I wanted to round this up with, this is one of the main reasons why we couldn't just run HTTP2 on top of QUIC. Because HTTP2 has streams.
Yeah.
QUIC also has streams. And so we would have like two different stream abstractions colliding, basically. And we tried to solve this with all kinds of hacks and workarounds. It just didn't work. So one of the big changes between HTTP2 and HTTP3 is HTTP3 doesn't know about these streams directly. It offloads that to QUIC internally, basically. But the concept is still the same, right? Like I said initially, the high-level feature, the idea of the multiple streams is still there. It's just a technical implementation that is changed.
For a long time, it was like TCP is the protocol, and now suddenly it's like UDP is the protocol. You've basically replaced TCP with QUIC, but you were forced to use UDP. So we're going to see a lot more UDP, I'm assuming. I mean, like you said, 25% or something already on the internet, right?
Yeah, exactly. So you're going to see a lot more UDP, but really it's QUIC over UDP, right? But yeah, at this point, for example, companies like Cloudflare, they track it. So radar.cloudflare.com, they show a breakdown of a lot of statistics. And one of them is HTTP version. And they get like 26 to 30%, depending on when you look at it. Another question I often get asked is, when will QUIC completely overtake TCP? When will it be 100%? And so what I think will happen is that we will grow very fast to like 50% QUIC, like within the year from the big deployments, because Amazon is now rolling it out. Azure is starting to roll it out. So within the year, 50%. And then it's going to take us about 10 years to go up to like 80 to 90%. One of the problems there is, of course, security. Like firewall administrators and network administrators don't like to allow UDP because it's often used in all kinds of attacks. That's one aspect. Even if they would allow QUIC over UDP, QUIC is so encrypted. Again, this allows QUIC to be flexible. This allows QUIC to evolve, but it also means that firewalls are almost useless for QUIC. They almost have nothing to work with. They either just have to trust that QUIC will get it right, or just drop it in its entirety. And that's not really fair. There are a lot of security features built into QUIC that help prevent this kind of attack, right? So a lot of UDP-based attacks are actually mitigated in several ways inside of QUIC as well. So it should be quite safe to use. But there, of course, will be a lot of network administrators saying, no, I'll rather be safe than sorry, and just block it entirely. So I don't think HTTP3 will ever get 100% deployment, or I should say QUIC will ever get like 100%. They will always coexist next to each other, or at least for a long time, for those reasons.
If a firewall blocks QUIC, do the browsers and the servers just renegotiate or negotiate to go back to like TCP?
Yeah, it's actually smarter than that. Browsers will open parallel connections. If they try to do HTTP3, they also do HTTP2 at the same time. If HTTP3 is blocked, it doesn't get through, then HTTP2 will just go through, and the user usually doesn't notice any interruption of service because of that.
So so the browsers and the servers work around that problem, which is great. Because I mean, I think the worry is, okay, so if browsers are going to QUIC, what happens? Do I have to go and change all my firewall rules?
But that is also kind of a downside, because that doesn't force firewall administrators to switch.
Yeah, exactly.
Because they could just, even if I block QUIC, it doesn't matter, because people will still be able to use HTTP2.
Does QUIC only support HTTP, or does it support other protocols?
No, and this is crucial, I think. It's a very good question. I think this is a crucial thing to understand. And also why we often make the difference between H3 and QUIC.
Yeah.
They are completely different, because QUIC is really a replacement for TCP, meaning you can run any type of application level protocol on top of it conceptually. We are seeing SSH over QUIC. We are seeing Samba over QUIC. People are talking about doing real-time video streaming over QUIC in various ways. So it's really intended to be a general purpose transport level protocol that can be used for many other application layer stuff, not just HTTP3. HTTP3 was the main reason, like the main use case that we had in mind originally, but it has evolved to be much, much more flexible. Again, very important to know, these things are not tightly coupled. QUIC is completely loose from HTTP3, even though a tighter coupling is possible and get you even more benefits. You can run basically anything on top of QUIC, but probably like with H2 to H3, it's going to require some changes to your application level protocol. You're rarely able to just take the application level protocol and run it over QUIC without any changes. So that's going to be a long-term process to see who wants to switch and how that can be done for individual protocols.
QUIC implementation, I see you've got IPv4, IPv6. It's similar, or do I have to like learn a whole different type of QUIC for IPv6, or is it the same kind of idea?
No, it's exactly the same.
Right. Okay.
Yeah. Just like with TCP, it's completely independent from the IP version used.
For years, we've been told to learn UDP and TCP as the two big transport layer protocols. Now it's going to be QUIC, TCP, UDP kind of thing.
Yeah, and that's from my perspective. I've been teaching this at the university as well. I've had some networking courses, and that's going to be a big challenge from my perspective. QUIC is difficult to properly understand. If you look at the RFCs for QUIC, those are 4 different documents, many pages to even understand the basics of how it actually works internally. You need a lot of baggage, and even then. So that's going to be a big challenge, educating people. And that's one of the reasons that I've been trying to push out a lot of videos and blog posts and Twitter threads to help people understand in a more simpler way, to help them understand the basics before digging into the really underlying complex stuff and really trying to use it. That's another reason why I think it will take a long time to get from the 50% to the 80%, because the moment people can't just flip a switch, for example, on a CDN like Cloudflare or Akamai, the moment people actually have to start manually using this, for example, in their apps through libraries or in their stuff, it's going to be much more difficult.
We've covered like 2 big advantages already: is faster connection setup and then head-up line blocking. Is there another big advantage?
So one of the most talked about features is called the connection migration.
Okay.
The common use case is what they call the parking lot problem. So let's say you are currently indoors. You have your cell phone, which is connected through Wi-Fi to your office, for example. But then you move outside to the parking lot. It's time to go home. You move out of range of the Wi-Fi, and your cell phone automatically switches over to the 4G network. And that works. The problem is, from a TCP standpoint, you suddenly switch IPs, because 4G network is completely different. And the way TCP connection works, it just looks at the client and server IP and the TCP ports. And the client ports and that client IP changes because we change networks. Any TCP connection you have in that instance is going to have to be shut down. It's not usable anymore, and you need to re-establish all your TCP connections from the start. So you need to do all the connection setups again. You need to warm up your congestion window to get up to better data speeds again, and so on. If you're doing something like, let's say, video streaming or a big file download or a game, for example, you will have an interruption of service that may or may not be quite large. And that's kind of the problem with TCP. So what QUIC does instead is it will use what is called a connection ID. So each connection is not just the IPs, it is also a unique number. And then when you move between networks, it will keep this connection ID the same. Because we keep that constant, even though the IP and the ports change, the connection ID is the same. And so the server knows, oh, this is actually the exact same client that I had before. We can keep on reusing the same connection. We don't need to do a new connection setup.
That's great. That's a huge thing. Yeah, that's huge.
Right. The way that works, by the way, is by including this connection ID in every packet. So QUIC's packet header is quite different from TCP's already, and it also includes this new field called the connection ID. And that's actually one of the few fields that are not encrypted in the QUIC packet header, because you do want middle boxes to be able to view the connection ID. For example, load balancers. They usually work on the IPs, and they keep the load balancing routing stable based on IPs. That no longer works here, so they need to be updated to use the connection IDs to keep the same connection going to the same backend server, even though the IPs change.
That's great. So from a client point of view, it's seamless, yeah? You go from your Wi-Fi to your 4G or whatever, and it just switches.
Exactly. It's probably not going to be 100% seamless.
Yeah.
Because we change networks, and we don't know how much capacity we have on the network. So what you're basically going to do is you're going to fall back to what is called slow start. If you were on a very fast Wi-Fi sending several megabits per second, you're not going to be able to keep on doing that on 4G. You're going to start slow again, try to figure out what capacity do I have. So it's not going to be seamless, but it's going to be much better than over TCP.
You're not resetting your connection. I mean, that's huge.
Exactly.
Yeah.
Exactly. And that's already a big one.
What about hackers? Because is that connection ID not exposed?
Oh, and that's the question, right?
Yeah.
Because the connection ID is exposed. If you would do it exactly like here on the right side, you could have big hackers, let's say nation states or big companies that have a lot of different points of observing traffic. They can actually start tracking users geographically across different networks. We don't want that. You set up a connection on Wi-Fi. Once that is encrypted, so no one in between can see what's happening, QUIC is going to negotiate new connection IDs. Those are exchanged in encrypted ways, so in the encrypted QUIC connection. So the middle boxes, the observers, don't know about these. But the client and the server, they do. So basically, every connection is mapped to several connection IDs, not just one, it's several. And so when you switch networks, you just switch to the next connection ID as well. So here we're not reusing the green one. That would be very unsafe. We switch to the purple one. And the client and server know purple equals to green because they've negotiated it. But no hacker in between knows this because the negotiation was done in the encrypted connection. In the QUIC RFC, they call it the linkability prevention. They can't link different connections for the same user on different networks. This helps against hackers. And then in practice, it's even worse. This is one of the reasons that connection migration is it's very badly supported at this point. No single large deployment actually does this yet because it's really quite difficult to do. It's actually asymmetrical. So the client and the server, they use different connection IDs on their legs. So the client uses one connection ID value and the server uses another for several deployment reasons that I don't really want to go into. But basically, you no longer have like 3 connection IDs mapping to the same connection. You suddenly have 6. And in practice, you don't have 6, you have 32. All different numbers mapping to the same connection. To make deployments easier, for example, they use this to make it easier to do load balancing or indeed also firewalling. This is why these two are split up. But this makes it much more difficult to implement a track to figure out what is going wrong. And so connection migration has some potential benefit if you're changing networks, but it's really not that well supported yet. At this point. Sometimes people call this one of the big performance features of HTTP 3 as well. I don't really agree with that as much because to get benefits from this on H3 level, you would have to switch networks as you are loading a web page, which doesn't take all that long usually. I think this will be much more impactful if you're doing other use cases like I said, downloading a large file, doing video conferencing, doing gaming over QUIC, that kind of stuff. There is where we will see the big changes, not so much the HTTP 3 web page loading use case.
At the time of this recording, it's only been 3 weeks since this was standardized. So it's still early days. But like you said, 25% of the internet approximately is using a lot of this stuff. So you can imagine, I think, now that it's standardized, people who write applications for downloading or, like you said, gaming, this is going to make a lot more sense. And we hopefully see a lot of really cool applications coming out. I think the concern at the moment is like, as a user, do I need a special browser or do I need the latest iPhone or what do I need to actually do this, or does it just happen like in the background?
It's interesting you use an iPhone as an example because that's like the exception to the rule.
Okay.
The thing is, because QUIC is so encrypted, the idea is we only need to update the client and the server. So you do need to have like a specific server deployment if you're using Apache or Nginx or Node.js or something like that. Not all of them already support this. So you need a compatible server, that's one. Most of the browsers support it. You have Chrome, Firefox, and Edge have been supporting it for quite some time. Safari, very funny story, they were the first ones to implement it 3 years ago, I think, the very first ones to have full HTTP 3 support, but they have kept it behind an experimental flag. So not enabled by default, you have to enable it manually. And they've now slowly started to enable it by default for some of their users starting iOS 16. But so that means for iPhone specifically for Safari, you do need iOS 16 to be able to use it without manual action. But for all the other browsers, you just need an updated version of the browser. And updated here means literally a year old. That's how long it's been enabled already. That's for the browsers. If you want to start using this in your own applications, let's say you have a native app, that's more difficult. They would need to download an actual library, software library to do this because none of the operating system kernels already have QUIC support at this point. QUIC and HTTP3 are just user space level implementations at this point. Again, to keep them flexible, eventually they might move to kernel level implementations for performance as well. But for now, it's all higher level. This means you can easily drop in a library. As long as you have UDP access, you can start using QUIC and H3. But again, using those libraries is probably going to be quite complex.
I love the way that you guys use UDP because like you said, like I could use Linux, Mac, whatever, because they just see UDP.
Yep.
You guys can do all kinds of interesting things and make it better in the background without trying to rewrite every operating system out there.
Yep, exactly.
You mentioned Facebook, it's Google. Is it the big companies that are using this and that's why such a large portion of the internet is already using it? Is that correct?
Yep. I think that's a very good statement. All the big deployments like the content delivery networks, the CDNs, were one of the major pushers and contributors to this. So they have enabled it en masse. Google obviously, all the YouTube, all the Gmail stuff is on there as well. Facebook, we have Microsoft starting to push it now. Amazon is jumping on board. It's basically the bigger companies, and that's one of the, I would say, sad things about the modern internet. We are relatively centralized, and this means if just the big companies enable it, we will get to that about 50% mark quite easily, right? Because they just have such a big share of total traffic. Yeah.
A lot of people will say that's a problem. I think you've said this in other articles. The internet's so centralized among a few big companies.
Exactly. This is something I want to push back against. Some people have been claiming that this is all a Google thing, right? And it's like a conspiracy from Google, and Google has been pushing QUIC and H3 because of their own nefarious purposes. And that's not true. Like, it started at Google, but the original Google QUIC, as it's called, is so different from the current QUIC and HTTP3. Because QUIC and HTTP3 have been contributed to, like I said, by other companies, and not just the big bad ones, like you might say, browser, Facebook or Meta might not be your favorite companies either, but like Mozilla. Mozilla has been a major contributor to QUIC and H3, and I think you can hardly argue that Mozilla is trying to fight your privacy or something, right?
No, that's a good point. Are there any like other cool highlights that you can show us, that other things that we perhaps should be aware of?
So there are two other main things that you should be aware of. One of them is called header compression, or as they call it now, field compression, because they renamed headers to fields. So the idea is you don't want to send your headers, or at least your header values in plain text, over the wire, because things like cookies, for example, or some of the security headers nowadays are getting quite large. And what you want to do, because those values are usually the same in every request and response, you want to compress them. You want to send them once and then reuse a reference to them at the time. This is also in HTTP2, where it's called HPAC. And so now it's over QUIC, so it's QPAC, even though it's HTTP3. That's another one of the reasons that we needed H3 instead of H2, because QPAC, this header compression stuff, is a lot more complex now, because we have those independent streams at the QUIC layer now. Again, a bit technical to explain why, but this was actually one of the most difficult things to do to get right for HTTP3. We might show Wireshark at the end of this. Wireshark doesn't yet do QPAC decoding at this point. So you can't actually do full HTTP3 introspection with Wireshark yet because it's so complex. And there are very few implementations that do like full QPAC. Most of them do like a basic version of it. There is like a standard version that gives you, let's say, 70% compression benefit, and the full version that gives you the 100% benefit. But the full version is much more complex. And I think only Google, Facebook, and a company called Lightspeed have like full implementations for that at this point. But this is something you will see pop up. I hope you never need to implement it, because it's crazy difficult. It just means for like some tooling like Wireshark are still suffering from its complexity. Yeah.
If I went to Google, you said they're implementing this. If I was using the latest version of Chrome, it might be doing this in the background, right?
It is definitely doing this in the background. Okay. So you need to use the basic version. You have to use it. You can't use HTTP3 without this. If you want extra performance, you need the advanced version, and almost no one is using that at this point. The last feature that was also in HTTP2 and that is still in HTTP3 is called server push. And the idea from push is illustrated here. You do a request for, in this case, the HTML. If you do this on a CDN or like a proxy, it sometimes has to forward this request to a different origin server, and that can take a while. So here it takes a long while for the actual get for the index.html to get finalized by the origin, right? And so you have some time in between. They call this server think time, of server in between time. During that time, why wouldn't you be able to send other stuff back towards the client, right? And so that was the idea of push. You request your HTML, that will take a while, but you already start sending the CSS and the JavaScript because you know the browser needs this. You kind of fill in the think time with something useful. That was the idea. In practice, it turns out that it's very difficult to know which resources the browser already has cached, and so which you actually need to push. Because it could be that the browser already has your CSS and JavaScript, you just don't know it, and you're basically sending useless data over the wire. And there were other problems with push as well. And so push was kind of deprecated. Chrome has actually actively disabled it. It is still in the HTTP3 spec, not because it's going to be used. Chrome will not implement this, they have said. It is mainly there to make sure that HTTP3 has all the features of HTTP2, even though they might not be useful for the web page loading use case. Again, often get this question. No, server push is still not usable. It's only in there for legacy reasons. There is something else you should use. It's called 103 early hints, which is a very similar concept, but uses a HTTP level mechanism to get the same results. So if you're interested in that very recent blog post from Cloudflare and Shopify on this, They're using 103 early hints to get this kind of performance benefit, so you should be checking that out instead of trying to use push in 2022.
You mentioned you had Wireshark, is that right? Could you show us some Wireshark stuff? Yeah, that'd be great.
You can use Wireshark to look at what QUIC and HTTP3 are doing quite well today. I know you had a video with Chris Greer originally on this, so people should probably check that out for the basics here. But so QUIC is going to start with an initial packet, which is basically the QUIC version of the SYN in TCP, and then the server is going to send back the replies. And as you can see here, the server is already going to be able to send back some HTTP3 data, even without 0RTT. And what is in there is actually metadata. It's not really as a request or a response. It's not really usable data for the user. This is mostly like control setup. So this is literally what it's called. It's a control stream, and it has a settings frame in there. The settings frame, for example, has a lot of QPAC related stuff. So it says how much space can you use for the header compression? How risky do you want the header compression to be in terms of head-of-line blocking? As we discussed, QUIC removes head-of-line blocking, but with QPAC, you have a risk of reintroducing it if you're not careful. This parameter is like a way to tune that. How much risk do I want to take? The server sends back this, and then two other things it does is opens the QPAC streams. These will be used to send like instructions to set up the header compression stuff. Again, you don't need to know what exactly is happening there, but you do need to understand here. We're already seeing HTTP3, but it's really just low-level metadata that we need to later use it, right? This is like the first round trip that I talked about. The client sends something, the server sends something back, and then the client is going to start responding. This is the second round trip, and you can already see here the round trip, the HTTP3. This is where the client is going to start replying with HTTP3 level data as well. So here it basically sends back the same settings frame, but from the client side perspective to the server. And then afterwards, we're going to see HTTP3 level data. This is the actual request that we're going to send. And this is where we get this problem that I talked about earlier. We can't actually see what's in these headers.
Yeah, I was going to say, it's all encrypted, isn't it? So you can't really see much.
No, this is not the thing. This is decrypted. If I didn't decrypt it, I wouldn't be able to see this.
I would just see UDP,
yeah, I would just say UDP and maybe QUIC, but we wouldn't know what is in there. This is actually decrypted, but I can't see what is in the headers frame because it is compressed with QPAC.
Oh, I see.
And Wireshark doesn't have QPAC yet. I should also mention this, it's coming. I think we only have to wait for a few more months for it to be worked on. Someone from Apple is actually actively contributing this. But for now, you should be aware, if you're trying to do this, it's very normal that you can't see what is in the headers. For HTTP2, for example, you will be able to see, okay, this is the status code, this is the content encoding, and so on, all the headers that you know and love. For H3, we can't do this yet, at least not in Wireshark. The same goes for the reply that we get back. Wireshark doesn't even show us the actual contents of the reply at this point. It will show us other things, like the frames that are going on. There are other types of frames. Like, for example, here we have a priority frame. That's what we talked about earlier. Those can also be signaled in frames, like you see here. You can use Wireshark to look at what HTTP3 is doing, what QUIC is doing, but not everything yet. And this was a connection set up without 0RTT. So it waits a while. It takes a full round trip before we see HTTP3 level data. So let's compare this with one that does use 0RTT, which is this one. As you can see here, the very first thing that the client sends, this is the very first packet the client sends. It's already 0RTT and it's identified as HTTP3. What it looks like on the wire, it's very interesting. It actually has two QUIC packets in it. This is why it says two. So one QUIC packet is what is called typical long header packet. So this is your initial packet. That is what we see before in the previous capture. But then the other QUIC packet, the second one that's in the same UDP datagram, is the 0RTT packet. And this one already carries HTTP3 level data that is being set up. And here is stream 0. So these other streams, 2, 6, and 10, are again the control streams and the QPAC streams. They use separate streams. But the stream 0 here is actually the stream that is carrying the actual request. Again, we can't see what's in the request, but believe me when I tell you this is an HTTP GET for Facebook.com. And so it is sent in the very first packet. The first thing the client sends contains QUIC, all the QUIC stuff. In here is also the TLS stuff. That's in the crypto frame. So this is the TLS handshake. The client hello for the start of the TLS handshake also includes HTTP3 level requests and other metadata, all in a single round trip. That is what I was earlier showing with the arrows. That's basically the same thing in Wireshark. And you can see that again here. You send these, and what you get back from the server, the first round trip from the server sends back 5 packets apparently here. You can already get HTTP3 level data back. It's already in there in the first response. And so that is how HTTP3 can be a lot faster than HTTP2 in practice.
I suppose from a troubleshooting point of view, a networking point of view, it's a bit of a nightmare because all you see is encryption. It's difficult to troubleshoot stuff unless you get the keys or the certificates,
Exactly. And that's very important to note indeed. These are decrypted. traces, right? So again, if you want to learn how to use that, David has other videos on his channel that explain that. This is already decrypted. If you are not using decryption, you basically see almost nothing of this. Your Wireshark is just going to show, oh, I don't have the keys for this. This is just random data for me. You won't even see, it won't even show here that it's HTTP3. You will only see that it's QUIC, because it doesn't even know that. And that is annoying for you as a user, as a network administrator. It's very difficult to know what it's doing, because if you are, for example, taking packet captures on a load balancer or on a firewall or anything else inside of the network, you won't have access to these encryption keys. So it's very difficult to get anything useful out of QUIC and H3 that way. And that's one of the big challenges we will have. And again, why I think a lot of network administrators won't allow QUIC or H3 on the networks en masse, because it's so difficult to view what it's actually doing on your network.
But I suppose it's good to know, because let's say you're trying to troubleshoot issues on your network and all you're seeing is encrypted stuff. It's good to know that if we block QUIC, the browsers will, well, I mean, who knows what we're going to break, but hopefully the browsers will go back to using HTTP2, and then we can actually see stuff.
For now, the browsers will indeed fall back. But please, please, please don't take that to mean that you should all be blocking QUIC.
Exactly.
I did not say that. Like I said before, there is very few reasons to be afraid to allow this, even though it uses UDP. QUIC has a lot of security mitigations built in. If you are worried about specific types of attack, read about those first and then decide whether or not to allow it.
Already 25% of the internet's using this, or traffic on the internet. So it's already here. It's not like you can ignore it. It's already here. The big companies are pushing it.
That's exactly true. And while for now you might still have a very simple fallback, I definitely can see bigger companies like Google or Facebook starting to disable HTTP2 over TCP over time to try and force people to switch to that. We're definitely not there yet. Not enough people support it, but I can definitely see that happening in 4 to 5 years, let's say.
Robin, I want to thank you so much for sharing. You've shared so much knowledge with us. Thank you so much for, simplifying it and, coming down to like our level. Really appreciate you doing this.
Yeah, no, thank you so much for having it. Like I said during the talk, this is so complex. And if people just have to start from the complex documents that are out there, it's going to be very difficult for people to get anywhere near what they need to be actually able to use it. And that's why I've been trying to do this kind of video and my own blog posts, is to get people at least to a basic level of understanding that they can then bootstrap themselves to start using it a bit more. So thank you for giving me this opportunity to share this with your viewers as well.
I appreciate it. And where can people find you? Are you on Twitter? Is that a good place?
I'm mostly on Twitter. My handle is @programmingart, and I will also be starting a new blog soon. You've mentioned my blog a couple of times. It's not really my blog. I have like many different blog posts in many different spaces. I'm going to start my own blog soon.
No, that'd be great.
To kind of consolidate all of that.
Yeah. I mean, the articles that you've written are amazing. For this interview, I read some of the ones that you recommend, and it's great because you explain it. I think it's great that you've done it like in video format, like now, trying to keep it simple, and then people can go and read your articles, which I'll link below. And then if they've got questions, can they shout at you on Twitter? Is that right?
Oh yeah, absolutely. Please do. I love interacting with people on Twitter about this, and seeing other people from the QUIC and HTTP3 join in, and they often give a lot of good answers as well. So if you have any questions, please reach out. We are more than happy to help.
That's brilliant. So Twitter's the best place. Are there any other places that you'd recommend?
I'm also on LinkedIn, of course. And if you really have some very specific stuff, you can also reach me on my email, which you can also easily find online.
Brilliant. Robin, thanks so much.
All right, David, thanks. And see you all later.